example, we work with on a packet radio internet system, right?
Yep.
And every 1980s or late 1980s, and he was with IISc started a company also, and then also worked with Sequent, Sequent had an operating system called Dynix PTX. Even I know something about Dynix PTX because I worked with kind of people called Veritas, and Veritas and with connection between Veritas and Sequent, and that's how I came to know something about great amazing synchronization mechanical connected with Sequent. That's how I heard about it. Okay? The Veritas people would tell me a lot about how amazing Sequent was when it comes to synchronization.
It was a lot of fun.
Right? Yeah. And what is very interesting for us is that the same mechanism we developed for Sequent has finally made it to Linux with an interesting twist. Again, I learned this from talking to sometime in the recent past. He says that the mechanism invented in Sequent was sort of one of a kind. It stayed safely for a long, long time. It didn't really evolve. The minute you put it to Linux, people in Linux kernel used in so many different ways because it was sort of, I shouldn't say open source, because it was not created with it, right? It was created.
I learned more about RCU in the first 3 years of working with Linux community than the previous 7 years working on it at Sequent.
The question is, you had the Sequent had patented
oh yeah,
PC, right?
yes.
So it means it expired by the time it came to Linux?
That had not actually. It had not.
It became public, is it?
Well, if you look at the GPL, Linux is covered by the GPL. And one of the terms of the GPL is that if you make code available under GPL, you're not just making it available to who you gave it to. So if I gave it to Professor Gopinath, I'm not just giving the code, I'm giving him the right to also change it and give it to anybody else. In other words, I'm giving him all the right with respect to that code I have, essentially. And that means if I hold a patent and I give him the code that does that patent, I'm giving him a patent license.
Yeah, but Sequent had no problem because we are part of IISc.
That's right.
So people that know was a patent, it became publicly available to everybody so that nobody would be violating the patent which is used.
As long as you use it in GPL or LGPL.
Very fast understanding. And what's interesting to me is this amazing insight that you just mentioned, that in 3 years of his use of RCU and Linux, okay, it was subjected to so many different users that it broke every single principle of original design in Sequent.
Pretty much.
And I had to fix it, and I still fix it because it's being used for so many different. For example, somebody somewhere in Sweden or someplace they used it for a router, and the routers actually use I think at much higher rates at which things are synchronized or changed. And so whatever basic premises they had made in the original RCU was really not really valid, right?
Well, what happened was at Sequent, what we did is we said, okay, we've got a firewall, and that'll protect us from DOS attacks. When you're Linux, you are the firewall. You can't hide behind a firewall. So we had to, as you say, take whatever they gave us.
There were some interesting attacks on the system which actually had to be fixed. So he's going to talk today about RCU. So it's a very fascinating talk. He also has written a paper in ACMQ. If you want to read a slightly more elaborate discussion on the same idea, it's there in ACMQ of this month.
Yes, May 1.
Yeah, it's a May 2013. So that introduction I'd like to request Paul McKenny.
Thank you, Professor Gopinath. So yeah, it's been quite a bit of fun, and it's been quite a interesting journey. So I hope that you guys have as much fun with this or whatever as I've had with RCU. I didn't think it was legal for guys my age to have as much fun. Probably isn't. So just what is RCU? And we'll talk a little bit about mutual exclusion, some example applications motivate this, and so on through areas of applicability and summary. So let's talk about mutual exclusion a little bit. I'm going to make an assertion, and I'd like to get people to vote on whether they agree with the assertion or not, and then we'll look at it again a little bit later. The assertion is we simply do not have a synchronization mechanism that can enforce mutual exclusion. How many people agree with that? Okay. How many people disagree? Okay, we got a few. How many people don't care? We got some people. Or how many people just didn't feel like voting? Okay, so most people think we do have synchronization mechanisms that can enforce mutual exclusion. Okay, remember that, and we'll get back to that later on. So let's take a look at an example application. And what we're going to do here is we're going to look at Schrödinger's zoo. So he's got this zoo, and he wants an in-memory database to keep track of the animals in his zoo. And so, for example, if an animal is born, that results in an insertion. You have to have a record in the database for the animal. If the animal dies, then you remove the record from the database. And he has a lot of short-lived animals, for example, mice. And so he has to be able to handle a very high update rate. And in addition, there's just an amazing amount of interest in the health and welfare of his cat, okay? And he thinks maybe it's because all the mice are interested in acquiring it. But of course, we know that there's some perhaps other interest in Schrodinger's cat from the physicists around. It's probably kind of hard to see there. It says, being simultaneously dead and alive in the box gave me an incredible perspective over life, the universe, and everything, and I'm here to tell it to the world. So there's a lot of queries that come in for his cat, and the in-memory database has to handle this. So going back there, one approach we could use, a really simple approach, is just to have a hash table with chaining and to have a lock on each hash bucket. And that means that insertions, deletions, lookups happening in different buckets can proceed in parallel. And also, we should be able to handle a high update rate. And here's an example how that might work. We've got, in this case, we just have 4 buckets. We have a lock on each one. With the mouse and the zebra happen to hash to bucket 0. And the boa, the cat, and the GNU happen to hash to bucket 2. Okay? And so we can get fully parallel access to the mouse at the same time as the boa. But of course, if somebody's looking at the mouse and the zebra at the same time, they'll be serialized on this lock. Okay, pretty straightforward stuff. So, those of you who said that we do have a mutual exclusion mechanism, I've got another question for you. Will holding this lock right here, will holding that lock prevent the cat from dying? If that really did work, I think I'd acquire my lock. So it depends on what you mean by mutual exclusion. When I asked you that, the people that said, yes, we do, were thinking just of inside the computer. There's a big world out there, and a useful computer program has to interact with the world. And your ability to synchronize or mutually exclude a large part of the world is limited. The world's going to do what it's going to do regardless of what your program thinks, for the most part, unless you happen to have something fairly impressive attached to your computer, like a big hammer or something. So let's just put this on a computer and fire it up and see what happens. And what we're doing is we're just doing lookups. So we're not doing updates, we're just starting simple, starting slow, just doing lookups. We've got a system with up to 60 CPUs, and this is an x86 system. We have it's 2 gigahertz, and we also have simultaneous multi-threading. So there's 32 cores, and that means once we go beyond 32, we're starting to share threads. And that's why we've got this little bump up right here. But as you can see, something pretty bad happens once we go above 8 CPUs. The drop-off is really catastrophic. Any guesses as to what bad thing is happening there? Why? I mean, this is a hash table. We're looking up. It's fully parallel. Why is the throughput dropping from 50,000 down to less than 15,000 as we go above 8 processors? What's happening? Come on, take a chance. Okay, so that's a good guess. We happen to have a system that has each socket has 8 cores, and we start off with 1 thread per core. And so as soon as we get past 8 threads in this, suddenly we're going across sockets. And in fact, there's another possibility as well. That is a very good one. What other effect might we be running into? Lock contention. As we increase the number of, we've actually got quite a few. We got 1,024 hash buckets, but nonetheless, as we increase the number of threads, we've got to increase the probability that they collide. So let's take the second one first, just to be out of order. I mean, after all, we wouldn't want to order things too much. And let's try adjusting the number of buckets in the hash table, increasing it, and see how things work out. So each line is marked with the number of hash buckets, and so this is our original curve here that we saw before, going up to about 50,000. And we doubled it again, and yet again. And as you can see, we're doing quite a bit better. We get better throughput. There was some contention down here, and it's being relieved as we increase that. But we've still got a big spike at 8 CPUs, and it drops off after that. And quite frankly, this is not the kind of scalability that Schrodinger needs for a zoo. He needs to do better than this. So let's take a look at the second reason. And that would be the NUMA effects, the fact that we've got 8 cores per socket. And what that means is we got a socket here, we got a socket here. We just have 8 CPUs used. They stay within this socket. The memory latency is very low. There are no NUMA effects, or very, very light NUMA effects, I should say. If we go above 8 CPUs, we use that 9th core, suddenly we're having to ship the locks. Remember, we're acquiring a lock, even though we're just looking up, back and forth across those sockets, and that should slow down. And in fact, if you go in and you look at the appropriate things in this on the CPU, we've got CPU 0 and 32 are sharing a cache. They're the same CPU, just the first thread and the second thread in the core, and so on for the rest of these guys. And then if we look at the third level cache, we've got 0 through 7 and 32 through 39. 0 through 7 being the first CPUs in the core, and then these are the second threads, hardware threads in that core. So that would go along with Professor Gopinath's suggestion. So let's try just running only 1 CPU per socket and see what happens. And again, we vary the number of hash buckets, 1024, 2048, and so on. And at this point, we just have 4 CPUs because we only have 4 sockets. And as you can see, it scales a little bit, but not really all that well. And we've only got 18,000 up there. Remember before, even if we only had 1,024 hash buckets, we got up to 50,000. So we were up about 3 times as high. So this just isn't the kind of scalability. Again, this isn't what Schrodinger wants for his in-memory database. He wants to scale a lot better than this. So let's look at why this is happening. I mean, some of you, I think, have a good idea when you talked about the sockets, but let's take a look more numerically at what's going on. So this is an older CPU. This is an Nehalem. And what we've done here is we've measured a number of operations fairly carefully. So the clock period is 0.4 nanoseconds, 400 picoseconds. And the ratio column is just the ratio of the cost of a given row to that of the cost of a single clock period. Now, so the best case lock we have is costing us almost 2 orders of magnitude more than a simple instruction. But what's worse is if we have an off-socket cache miss, we're way above 2 orders of magnitude. All right? So again, if we stay up here, we're within a single core. Down here, these 2 rows are within a single socket, but off-core. The ones at the bottom are actually going from socket to socket. And this was a 2-socket system. And so it's in a sense a best case. And the reason it's a best case is that if something comes off of one socket, you know it has to be going to the other one. Whereas in the other system, we had 4 sockets. So you come off a socket, you got to have something to decide which of the 3 other sockets to send it to. So the other system was probably worse. So one thing you could hypothesize is that the reason it drops off is because suddenly we're faced with these very expensive operations as we ship data and locks from one CPU to another. Okay, so so one thing is, these are really low-level details. Why should we be worrying about numbers of cycles and things like that? We've got great abstractions we could use, right? And these are some reasons I assert that we need to pay attention to it. How many people here know what the steel alloy transition temperatures mean? We found out about, the human race found out about steel alloy transition temperatures the hard way. During World War II, there was a lot of shipping going across the North Atlantic. And of course, there was losses due to submarines. And there were a lot of ships that would set out and not get to the other end. And they were rather impressed with how effective the submarines were at torpedoing ships until one day, one trip, there was a crack that opened up on the deck plate. So you get on the top of the ship and you're in there and there's freezing water and this crack is just kind of going across the top of the ship. And they tried welding in front of it and all that did was make the crack go faster. And suddenly it hit another plate of steel and it just stopped. And so they came into port with this crack, fortunately on top of the ship instead of underneath. At that point, they decided to look more carefully at how steel worked. and they found that depending on the exact composition of the steel, you'd have a transition temperature somewhere, it's like 40 degrees below zero that it would happen. But below that, and that temperature would vary depending on the exact composition of the steel. So some might do it at 30 below, some might do it at 70 below. And once you got below that temperature, whatever the temperature was for your particular mix of steel, it would become very brittle. And that would mean that instead of just flexing when the waves bashed against it, it would crack and break. So I suggest that you should not be on a ship that is designed by somebody who ignores the very low-level detail of the steel oil transition temperature, steel alloy transition temperature. I mean, it's your life, do what you want, but my suggestion would be that you should really have these people pay close attention to that sort of detail when you're taking, and airplanes as well, all right? And the next one isn't so pertinent to Bangalore. You tend to make your houses out of concrete, which doesn't have this sort of problem. But where I come from, we make them out of wood. I'm not sure why that is, but that's the way we do it. The place I come from, it rains fairly. It rains a lot. 200 days a year it's raining, but compared to here, it's a dry rain. What I mean by that, and where I come from, you can walk out in the rain and most of the times and walk back in like this. You're still a little bit damp. You walk inside, you dry off, no problem. I wouldn't have tried that Saturday or Friday evening here. You guys have wet rain. We have dry rain. Anyway, if somebody's building a house in Oregon out of wood, I would really want them to know that wood rots when it gets wet and it stays that way for a long time. That's a detail. I mean, you might be worried about the abstract structure of the house more, but I think that the details of the material are important. Cars, they have exhaust. Exhaust is very corrosive. I'd like the guy designing the car to know that so that they use the right materials for the exhaust system so that the car doesn't fall apart. And of course, the most famous example is the space shuttle back in the 80s, where they ignored some of the low temperature characteristics of O-rings, and as a result, a number of astronauts lost their lives. So my question to you, if you're willing to grant that people designing these sorts of constructs completely understand the low-level details of the materials they're working with, might you want to consider people designing computer programs? Maybe they should understand the low-level details of the machines they're running on, at least if they want them to run fast and have good real-time response and so on. And yeah, there's a lot of systems where you don't care, but there's a lot of computers that your life depends on anymore, like the ones in your car and any number of other computers controlling things. I think it'd be good if the people designing those paid attention, not just to the abstractions, but to the low-level details of the machines they're running on. And I would suggest that you might not want to trust a parallel algorithm written by somebody that did not understand this. And for the examples, and for the reasons shown on the charts earlier, where the throughput just dropped off catastrophically. All right, but the other thing is that, why is this happening? What do these really mean? What does it mean for us? One thing it means is that abstractions like locks can have some interesting effects. So when we acquire the lock, if some other CPU held it, which if you have 60 CPUs will be the common case, all right, if you're randomly accessing a hash table and 60 other CPUs are randomly accessing it, when you acquire that lock, it was probably acquired last by somebody else. In that case, you're going to pay a cache miss just to get the lock data structure onto your CPU. And then you're going to have a single instruction that acquires the lock, and maybe the release is fast if nobody else got the lock in the meantime. So if you have a critical section that's just one instruction, you're paying a lot to do that. And if there's contention on the lock, so that by the time you acquire it, this is a long time, 256 cycles, maybe somebody else decided they want that same lock around out here. Well, it may well be that you have to get the lock back to release it as well, depending on the fine details of the machine you're running on. Let's think some more about this. Let's look at what this really means. In this case up here, where you have 256 cycles to acquire the lock, it's going to take 258 CPUs running in parallel, even with perfect scalability, to equal the throughput of a single CPU running without synchronization. 258 CPUs just to catch up with a single CPU. Down here is 514. And this is something that's perfectly scalable. Well, what this means is you can't just look at the scalability. You need to look at the overheads as well. And this is when we're not spinning. If we are spinning, then who knows how bad it is, right? You're spinning for some length of time, waiting for the lock, and then it takes you a long time to get it. And that was an exclusive lock. A reader-writer lock, you're going to have to acquire the lock. You're going to have to modify the thing, and this can take a little longer, so you have to read it, and then you have to read it again. And so on some systems, not this one, this particular one is nice that way. It looks ahead when you do the first read of the value and figures out that you're going to modify it, so it gets it modified initially. But there are systems that don't, and this would double in that case, because you're going to load it, and you're going to read-only copy of it, then you're going to try to update it, and you're going to have to take the cache miss overhead again. But here you can see you're having 800 CPUs to break even without that effect. And that's one of the reasons why reader-writer locks aren't used as much as they used to in the Linux kernel, because of this kind of overhead, this kind of effect. Yeah, it's read parallel sort of, but it's taking us 800 cycles to acquire and release the lock, and we only have one cycle. And this is the real work, and as you can see, they aren't in parallel. They're happening at different times. Okay, but locks. People know locks are bad. I mean, there have been huge numbers of papers written about how horrible locks are for a long time. But what about atomic operations? This is a single variable, and we're going to have all these CPUs doing an atomic increment on it simultaneously. So as we go across on the x-axis, we're adding more CPUs. The y-axis is the time that each CPU sees as the overhead of the latency of the instruction to do that atomic increment. And as you can see, it's getting quite long, and it's just getting larger as we add CPUs. Why is that happening? I mean, it's an atomic instruction, a single instruction. Why is it so slow? Why is a single instruction taking 2,500 cycles? The hardware has to mediate yeah, that's true. So let's take a closer look at that. This is kind of a cartoony picture of a computer system. So we've got CPUs, we have a store buffer, we have some cache here, we have an interconnect, memory hanging off of it. And this thing is physically not small. Let's suppose we've got one that's running at 2 gigahertz. Speed light in the vacuum means that you can go about this far and back in one cycle, in one 500 picosecond cycle. Well, that's quite a ways, right? I mean, chips are only about this big, right? So what's the problem? Well, part of the problem is that we don't use light in a vacuum to communicate data inside of our computer chips. Instead, we use electrons. About the best you can hope for an electron is about 1/3 the speed of light. And that's going through a wire with everything, with the wind at its back, essentially. More like, if you're going through transistors or any kind of active circuitry, it's more like 3% of the speed of light. So at that point, instead of 7.5 centimeters, we're talking something much smaller. We're talking about something smaller than the size of a chip. That means that in a cycle, we can't get from one side of the chip to the other. It takes many cycles to get data from here over to here, just because it takes electrons a long time to traverse that distance. What that means is if we have the atomic increment back to the hardware mediation point, which is a good one, what's going to be happening is that the cache line containing that counter is going to circulate through each CPU around the system in a big loop in red there. The more CPUs you have, the longer a path that piece of data is going to have to travel as each CPU increments it along the way. And that's why we were seeing the time just keep going up as we were going through things. So we have a huge amount of latency involved with this kind of atomic operation. What you want is something more like this, where your CPU operates on its own data, and doesn't have to move. It can stay in the cache and in the store buffer. At that point, you can go at extremely high speeds and have very little latency. So we'd like to be over here. And that's the same, if you remember, on the diagram. That's being up at the top with the fast things instead of down at the bottom and the slow things. In theory, you could do better with increment. Increment's commutative and associative. What you could do is have this interconnect realize, geez, all these guys want to increment by 1, so I'm going to send a request out to increment by 4. And eventually it finds the data, increments it by, in this case, 16, and then arbitrates out who thinks it has what value when you come back. And that's going to be a lot faster. You're going to have essentially the log of the number of CPUs in tree depth there. But it's still a lot slower than having each CPU operate on its own data. SGI systems used to do something like this back in the 90s. And I have some reason to believe that some of the AMD systems do that now, are starting to do that now. The Intel systems clearly aren't or weren't as of the Westmere generation. So we got a couple problems with physics. One of them is the finite speed of light, or in our case, the even more finite speed of electrons. The data just can't go faster than the medium that's carrying it. The other problem we have is that atoms are non-zero size. And this is, they've actually built transistors in research labs that are like this, where the base of the transistor, you got a source, a base, and a drain, switches back and forth across this, where the base is really 1 atom thick. I don't know how thick they are in this laptop right here, but I've seen scanning electron microscope pictures of them from about 7 years ago, and they were about 5 or 6 atoms thick. So you can only make them so thin. The thicker they are, the slower the transistor runs. And you can do something by having a dielectric constant, but your dielectric constant is limited by the materials you can use, and the materials are limited by the process and how you have to do it, and the fact you have to make billions of these things. So if you're into physics, there's the 2 really cool problems for you to solve. Make the atoms smaller and make light faster. In the meantime, I hope you guys get on the stick and really get those physical constants taken care of. It'd make life easier. But in the meantime, we have to live with them. And so how does the software live with hardware that has to live with the laws of physics? One design principle is to avoid bottlenecks. If you have pretty much one of anything, a single global lock, a single variable you're atomically incrementing, or a single variable that's affected by all the transactions in transactional memory, you end up with something like this. All the CPUs are trying to do the same thing at the same time. You end up with it piling up and being slow. What you'd like is to have more than one of everything. This works better at scales. But the thing is, that's exactly what we did on that hash table earlier. And we still had negative scalability above 8 CPUs. So this is good, but for large systems, it's still not perfect. It's not good enough. And what happened is the NUMA effects, the cross-socket traffic, defeated the scalability. It was still scaling, but it was scaling really slowly. So the other design principle is to avoid expensive operations. A lot of synchronization primitives do this stuff a lot. Compare and swap on global variables, any number of things like that. Software transactional memory implementations tend to have single counters they increment. What you want to do is you want to be up here. So it's kind of like the doctor. You come in and say, doctor, it hurts when I do this, and the doctor says, don't do this. Well, that's what we're talking about here. It's slow if you do the stuff down there, so don't do it. Do the stuff that's further up. There's a couple ways of approaching this. One of them is to say, if synchronization is expensive, use large critical sections. In other words, if you're going to pay an expense to acquire a lock, or increment a reference count, or enter a transaction, or whatever you're doing, get your money's worth. Do enough work in that, protected by that, that the overhead of the synchronization reduces down to almost nothing. So the idea is that off-socket is about 260 cycles, so let's just have a 226,000 cycle critical section. At that point, our synchronization overhead is 1%, and at 60 CPUs, it's negligible. It'd be really good. Except that we want to keep contention low, and the standard way to keep contention low is to keep the critical seconds short, right? So we have kind of a conflict in what we want to do. The best way to resolve this is in designing the application. One mistake a lot of people make is to try to apply parallelism at the lowest level on little dinky operations. The problem is if you parallelize a little dinky operation, you end up paying a huge synchronization cost for a little dinky operation. And that's where we ended up back there where we had our 1 cycle and 250 cycles of lock acquisition overhead. Instead, partition at the highest possible level. All right? So for example, I mean, the normal approaches here are the things that are embarrassingly parallel. And embarrassingly parallel, when you're parallel, is a really good thing. So what you want to do is to divide the application up into as big a chunk as you can with as little communication among the chunks as you can. And that way you can end up with no contention and also very little synchronization overhead. Monte Carlo simulation is probably the poster child for this. You just fire off separate instances of the program. They don't communicate at all. You just say whatever the programming is in ampersand in the shell. And then sometime later you say wait, and if they take several hours each to run, your synchronization overhead is nothing. I've had people tell me that's not parallel, and I'm not sure what they meant by that. I think they meant it wasn't complicated enough to be interesting parallel. But you know, sometimes boring is good, especially if it means you can go fast and scale. Another design principle is to avoid mutual exclusion. Here we only got 3 CPUs, but we talked about having 60. And in my role as maintainer of RCU and the Linux kernel, I've got bug reports for machines with 4,096 CPUs. All right? Well, if you're using mutual exclusion, you're saying, okay, we're going to write something here, we're going to spin for a little bit, and now we're going to update. And we're going to keep all the readers from doing anything for this whole period of time, and then we'll go back to reading. Well, if you got 4 CPUs, you can see that big red square is pretty big already. If you got 4,096 CPUs, you're really causing a lot of trouble with mutual exclusion. You're basically telling everybody to not do anything while you do something, and the whole point of the computer is for it to do something, not to not do something, right? What you'd like is something like this. You just like to be able to just do the update and have people read at the same time. Of course, you'd like your program to work as well, right? So let's take a look at that. How can you implement something like this and have it keep itself straight? I mean, if you're having readers and updaters all going at the same time, how can that possibly work? Well, let's just try it, right? I mean, sometimes you just have to go there. There was back when I was in my early 30s, I worked for Sequent, as Professor Gopinath said, and there was an older guy working the clusters thing, and he had a sign on his cube. And the sign said, "Only those who have gone too far can possibly tell you how far you can go." So let's just go all the way and see what happens, right? So what we're going to do is we're going to assume a non-preemptible environment. And my 2 primitives, the 2 read side primitives, are going to be # define, RC read lock, new line. If you're used to functions, just think of a function that doesn't have anything in it. You know, if you're in Java, just 2 curly braces. And # define, RC read unlock, new line. So we're talking lightweight here. Now, it's your guys' job to find something lighter weight than this. I'm an old guy, so I have to stop somewhere. But you know, you guys have to carry the work on and get up with something that does negative overhead. Let me know how it goes. Until you do that, until you come up with something like that, I assert that this gives you the best possible performance, scalability, real-time response, weight freedom, and energy efficiency. It's hard to do something faster and more efficiently than not doing anything. Now be careful, if you use that to justify not studying, you may have some problems with grades towards the end of the term, but I'll leave that between you and your professors. Okay, so this is ultimately lightweight, but one question you might have is, what do I do with this? In fact, some of you might be generating a proof inside your head saying that these things can't possibly affect machine state, and if they don't affect machine state, they can't possibly use synchronization primitives. Yeah, and you know, 25 years ago, I would have been right there with you. The problem with proofs is they rely on assumptions. And if you have a broken assumption in your proof, you get the wrong answer. But of course, I have to prove that. So the question that you should be asking me is, how can something that does not affect machine state possibly be useful as a synchronization primitive? Well, let's take a look. So let's kind of look at what we're trying to achieve, kind of an approach, kind of an overall abstraction for it. Since I've been complaining about it earlier, I might as well use them now. What we want to do is we want to publish new data. All right? If an animal is born, Schrödinger wants to publish the fact the animal is born so people looking up can find it. And we want to be able to subscribe to the current version of the data. If somebody wants to find out how the cat's doing, they should be able to get a record saying how the cat's doing right now and be able to look at it and see some reasonably consistent view of that data. And we also want to wait for pre-existing RCU readers. And the idea here is the trick we're going to try to do is we are going to do the updates carefully to avoid disrupting the readers, and then wait till all the readers are done. And when I say all the readers, I don't mean all the readers forever. I mean all the readers that started before we did the update. If they started after the update, they have no chance of seeing the thing we removed. And so we don't have to wait for them. We just have to wait for the old readers. And what we're going to do is we're going to have each reader continue to traverse its copy of the data, while a new copy might be created concurrently by each updater. And that's one way to justify the name read copy update. That's not the way that Jack and I got to it, but I like that approach better. My major prof, John Walpole, suggested it. Anyway, the idea then is once all the pre-existing RCU readers are done, you can't possibly have anybody accessing this old data that you made inaccessible, and therefore you should be able to get rid of it. So let's kind of go through pictorially how this might happen. So we'll just look at one data item to begin with. So we got maybe it's the data item for the cat's being born. So we have the cat pointer here, the C pointer. And what we're doing is these colors. A red thing is something that might be accessed by a reader at any time. And that means if an updater is going to mess with it, it has to be very, very careful. A green thing is something that only the updater has access to. The readers have no way to get to it. So if we allocate some memory, readers can't find it, at least if the memory allocator is working correctly, and they're using their pointers correctly. And so we've got this piece of memory with garbage in it, and we've got a temporary pointer to it from the updater. Now, we have to initialize the data, so we put in some fields for the cat, whatever they are. And still, it's only accessible by the updater, so we can just do that initialization anywhere we want. And then we can almost do this. We'll talk about later about why we can't, but we could just do an assignment. We could take the value of temp and store it into CPTR. And once we do that, suddenly this is accessible to the readers, so its color turns to red. And the readers are picking up the pointer to access it. And that's not quite right either, but we'll see why later. So what we've done, ignoring the little bits about those two assignment statements, is we have made new data available to the readers without disrupting them. Now, it's true that if a reader comes in about here, two different readers might disagree about whether the cat is there or not. On the other hand, exactly when is the cat born? I mean, if a cat's being born, do you count the time its tail comes out or its nose comes out? Do you count the time that it starts moving? You know, whatever it is, there's several seconds or maybe even a minute time there, so it's okay to have some uncertainty about when we add the record. Unfortunately, CPUs and compilers are highly optimized, is what they call them, and mischievous is what I call them when I'm using them. So let's look at this as code. So we allocated the data structure, we initialized it, and then we did the assignment. Okay? And the reader picks up the pointer and does something with it. Does something with the fields in the cat. Looks pretty straightforward. Unfortunately, both the compiler and the CPU are within their rights to rearrange things. So we've told this thing, the compiler, if it's a C compiler, is within its rights to assume there's only one thread going through here. And it says, well, I could do this publish, and then I could do these things later. That's okay. And the CPU could do the same thing if it's weakly ordered. The reader is even a little more diabolical. And there are CPUs that do this. The DEC Alpha is one of them. What it could do is it could kind of guess the value of the pointer. And then it could pick up the pieces from the pointer and call this function. And then it could check to see if its guess was right. And if the guess was wrong, it goes back and retries. All right? Of course, the problem with that is that it might guess wrong because it might guess the thing was just allocated up here just right now. And then it could go and call this function. Remember, it's not initialized yet, so it fills in garbage here. And then before it comes back for the function, these three statements could happen, and then we could assign the pointer. Which means that when this guy does the check down here, it says, yeah, great, we're in wonderful shape, after it's passed garbage to this function. All right? And there's one CPU that does this, and there have been academic papers on wanting compilers to do this. All right? And we don't want that to happen in this case. And by the way, this may sound really weird, but you can look at that web page down there. The slides will be available at some point, and see all about it.
Why would you want to do something like that?
Well, that was my question too when I talked to the alpha architects. In fact, I read the manual and I couldn't imagine the words meaning that it could do that, right? And it took them like an hour or so to convince me that how it really did that. And it took me like 2 hours to convince them that their documentation didn't make that clear. What happens, the reason they do that is that they essentially split the caches. And that allows them to have greater memory bandwidth because they can have multiple instructions in flight and they can be accessing different parts of the cache and happening in parallel. Well, and that's okay. Most machines these days do that. What the alpha didn't do was interlock ordering between them. And so what could happen is that the pointer itself might be in one of the caches and the data structure pointed to might be in the other. Okay, this isn't a problem because what happens is that you do the allocation. As soon as you do this right, that's going to invalidate the data structure itself, and it's going to send an validation request out using the cache coherence protocol. And then when it writes this thing, it's going to invalidate the other cache line. And in DEC alpha, you'd have to put a memory barrier here to make sure those happen in order, as you would on any weakly ordered machine. Problem was that on the read side, let's say they're going to different caches up the read side as well. And let's say that the cache that was dealing with the data structure itself was really, really busy. Then a whole pile of invalidates, a whole pile of reads out of it, and it's gotten behind. Whereas the other cache, the other side of the cache, the one that handles the pointer, is idle. And that means that the CPU at the other end, unless it does a barrier as well, can get the new value of the pointer and the old value of the data pointed to. Now, all machines except DEC alpha have some trick they use to prevent that from happening in this case. Okay? The x86 and other total store order machines, just the fact that you do it in that order, and the reads are ordered and the writes are ordered, so it just works out for you. As long as the compiler doesn't pull a trick on you, which it can, right? The compiler's still the compiler. The weakly ordered machines like PowerPC and ARM, what they do is they explicitly track the fact that there's a dependency here. Okay, the fact that you picked up this pointer and then you use the pointer to form an address, and they interlock those and force those to be ordered in that special case, and end up making it work that way. Except at DEC alpha, you actually have to have a memory. They all of them except for the TSO guys, x86, the IBM mainframe, Spark, and TSO mode, they have to have a memory barrier here, the weakly ordered guys. DEC alpha also needs a memory barrier right here. Okay, so what we do is we make it so instead of using assignment to pick up the pointer, we have a macro, RCU assign pointer. You have the pointer, you have the place you want to store the value and the value you want to store. And what it does is it puts the memory barrier you need in there for you and then does the assignment statement. Pretty straightforward. It's actually more complicated than that because there's error checking and stuff like that, but that's the gist of it. RCU dereference, what you do is there's a bunch of, this forces the compiler to just pick it up once. There's a bunch, if you let the compiler do it, it'll sometimes decide, well, I use it here and I use it here, but the register pressure is high here, so I'll pick it up and then I'll pick it up again, which would be really bad if you had people. Is use a vol cast to force it to pick it up. This thing is a no-op on everything except DEC alpha, where it's a read memory barrier, and then we just return the value. So we have these kind of wrapper things so that as a programmer using RCU, just say RCU assign pointer to update it, and you say RCU dereference to pick up a value. And then any memory barriers or compiler control that needs to be there is supplied by those primitives, and you don't have to worry about it. And again, the Linux kernel implementations are much more ornate because they have a bunch of debugging inside of there. Lock dependency checking and a bunch of other stuff like that. So what we do instead is we mischief-proof our code, which means we do just as we did before to allocate it and initialize it, but then we use RCU assign pointer to assign P to CPTR. And on the read side, we say P equals RCU dereference and CPTR instead of just P equals CPTR, and then we can use it safely. And if we use those, then those two primitives put together will force both the compiler and the CPU to do the right thing. And so this is the same diagram we saw before. The only difference is Then instead of CPTR equals P, we've got RCU assigned pointer there. And instead of P equals CPTR, we've got the RCU dereference here. So let's just do it. But on the other hand, all we're doing here is inserting into the data structure. And if all we can do is add animals when they're born, we'll have a big memory leak. I mean, we can mark them when they die. We just sort of mark them so they're ignored. But sooner or later, we run out of memory, and that's a bad idea. So we want to be able to remove things as well. So here we have the linked list. You remember we had our hash table from way back when we had the boa, the cat, and the canoe on one of the hash chains. So we're just showing just that hash chain. And the cat has died, and it's time to remove the cat. Now, these things are all red, and if you remember, that means that readers could be accessing them at any time. So there might be any number of people looking at the cat right now. We don't know. So what we do is we do list LRCU, and what that's going to do is going to take this pointer right here. There's a pointer, next pointer pointing at the cat, and we're going to put this value into it. Now that store has to be atomic, and this is something that RCU assigned pointer does if need be. It has to be atomic in the sense that if there are concurrent readers, they're either going to see the pointers of the cat or the pointers of the canoe, but they're not going to see some mush of the two stuck together. Either way, they'll see a valid list. At that point, we have something like this. Now this is yellow because only the old readers can possibly be here. New readers are going to bypass the cat and go straight to the canoe. This means at this point, we're going to have the readers disagreeing about whether or not the cat is alive. On the other hand, this is Schrodinger's cat, right? So that's totally reasonable. Anyway, we do synchronized RCU. What that does is it waits for all the pre-existing readers. So we have to wait for these guys. We don't have to wait for any new guys to come in. And the reason we don't have to wait for the new guys is because they can't get to the cat. Only the old guys can possibly be there. So once we've done synchronized RCU, and you may have some questions about how we detect that all the readers are done when they're not leaving a trace of their passage, we'll get to that. Once this happens, then we can safely free up the cat and leave us the list having only the boa and canoe in it, and thus have returned the memory so the memory can be reused so we don't just have a big memory leak. And again, as I mentioned earlier, if the readers aren't leaving any trace in memory, they don't have any executable code. It's just # define, RC read lock, nothingness. So how do we know when the readers are done? Any guesses? I gave one hint way back there. This, unless you have a really good memory, it's probably slipped your mind. And that is that we're working in a non-preemptive environment. Threads execute until they block voluntarily. They don't get the CPU yanked out from under them. No preemption ever happens. Okay? At least a couple of you are smiling. Maybe you have an idea. Well, let's take a look. And of course, one serious constraint is we don't want to introduce a whole bunch of overhead doing this. We don't want to force the readers to do a bunch of extra work. In fact, we don't want to force the readers to do any extra work at all. So we're going to define some terms here. We have an RC read side critical section, and that begins when you do RC read lock, and it continues when you get to matching RC read unlock. And there might be some RFU references in it. You can nest these things. So you might have a RC read lock, another RC read lock, and then you have to have two of RC read unlocks to come back out. We have something called a quiescent state, and that's any code that's not in an RC read side critical section. So if you're traversing the data structure, that data structure with the boa, the cat, the canoe in it, you have to be in an RC read side critical section. And that means you might be referencing the cat, if the cat's still linked in. If you're in a quiescent state, you're outside of an RC read side critical section, and in that case, you can't possibly be referencing the cat. You're not allowed to, just like the normal rules of locking. If you have some variable protected by a lock and it's protected completely by that lock, you aren't allowed to read or update that variable unless you hold that lock. So we have the same kind of rules here. We have an extended quiescent state, which is one that persists for significant time. We don't worry about that too much here. But the main thing is we have a grace period. And the grace period is some period of time during which every thread in the application has passed through at least one quiescent state. And the way this works then is if we remove the cat from the data structure and then wait for one grace period, then we know there can't possibly be any readers accessing the cat because all of the pre-existing RCU read-side critical sections have finished. And these names are nice, but I haven't told you anything about how to implement it yet, have I? So let's go back to the beginning. We're talking about a non-preemptive environment. This is like a Linux kernel code that's built with config preempt equals n. So there's no involuntary preemption. This means that the RCU readers are not permitted to block. All right? That's a rule we're imposing. So what we're saying is, okay, we're in a non-preemptive environment, and we're imposing a rule saying if you're in an RCU read-side critical section, you are not allowed to block. And that's not an unusual thing. If you have pure spin locks, you have that same rule. Because if you don't have that same rule, you end up with a self-deadlock. You have somebody spinning on you have somebody holding the lock, they block. All the CPUs get busy spinning on the lock. They can't have the lock till this guy runs. He can't run till they have the lock, and you have a self-deadlock. And the result is, if you have a pure spin lock, if you hold a spin lock, you're not allowed to block. And we apply that same rule to the RCU readers. Well, so what happens when you have a context switch? Let's say CPU 0 does a context switch. That means that somebody on that CPU blocked. And that means that any read-side critical section that happened before that has to be done if they're following the rules. You're not allowed to block inside a read-side critical section. So as soon as that CPU context switches, all the preceding RCU read-side critical sections have to be done. And then if you do that in turn on each CPU, well, let's look at what happens. So here we remove the cat. So time is moving from left to right on the diagram. We've got CPU 1, 2, and 3. These blue arrows are RCU readers, and the green circles are context switches. So we remove the cat. Now, that means that any reader past this point can't possibly get to the cat. But we don't know where these CPUs are. We don't want to coordinate that tightly because that's expensive, as we saw. So what we do is we do synchronized RCU. And that means we wait for a grace period. That means we do a context switch because we're waiting. Well, these guys go along executing maybe several. Now, we know from looking at this diagram that this RCU read-side critical section can't possibly find the cat. The cat is long gone. But unless we coordinate tightly, we can't really see that from a programmatic standpoint. So we wait until both these other two CPUs do their context switches. Once we get to this point here, all three CPUs have done a context switch since the cat was removed. That means that all prior RCU read-side critical sections have to be done. Therefore, it's now safe to free the cat's data structure. So let's go through that again. We remove the cat. There might have been some readers accessing it. This guy might have been accessing that cat all the way out to here. And this guy to here. The readers are not allowed to do context switches. So there's none of these green arrows inside these blue arrow things. That would be illegal. That would be a bug. Somebody would be misusing RCU. This guy does synchronized RCU, which is wait for every CPU to do a context switch. He's blocked. That means he gave up the CPU. There's his context switch. This guy executes along for a while doing whatever, and eventually, for whatever reason, does a context switch. So that means this CPU, all of its readers that might have had access to that cat have to be done. So this CPU can't possibly anymore have a read-side access to the cat. This guy does a bunch of read-side critical sections and eventually does this context switch, for whatever reason. And now we know that there can't be any read-side critical section on this CPU accessing the cat. So once we've got to this point, there are no readers with a reference to the cat anymore. We can safely free it. Any questions on that? No, we don't.
We have to wait for each CPU to do a context switch.
Mhm.
As the number of CPUs increase, then does this grace period increase dramatically?
Well, it could. It depends on, there's a bunch of things that happen there. One thing is that if you have a lot of CPUs, what will happen is you have some workload. And that workload has statistics about the distance between, the interval between context switches. And so if your workload happens to have a maximum delay between grace periods, that is the maximum time, the maximum time for the minimum grace period. Okay? But that's an excellent question. Another way of looking at it is, in this case, and there are other cases where it would be more problematic, in this case all we're doing is freeing memory. And if we wait a little longer to free the memory, if we have a big machine with lots of CPUs, we probably also have lots of memory. And if we wait a little longer to free the memory, who cares? They normally do the settings, last I knew, on the really big CPU, the really big systems, the ones 4096 CPUs, to be about 10 times as relaxed about going through grace periods as the smaller machines, for whatever it's worth. Yeah?
So I don't quite see how you prevent freeing memory allocated by someone else.
How I prevent freeing memory allocated by somebody else.
Yeah. Here.
Well,
Once CPU2 is in its grace period,
Yep.
let's say somebody comes and updates cache.
Well, keep in mind it's not CPU and it's grace period. The grace period is a system-wide thing, right? Okay? But as soon as CPU2 ends its grace period, or
I mean, how am I sure that I'm not freeing memory allocated by someone else?
why is that a problem? I mean, if somebody else allocated and added to the data structure, they're gone. It's just there. If I'm the one that removed it, the fact somebody else allocated, why is that a problem?
Okay, I'll think about it.
Okay. One possible reason you might not like that is because you might have NUMA effects, and having one guy allocate another free it might slow things down. But the correctness should be okay, I think. Okay. So the thing is, so we went back earlier. I was suggesting that somebody might consider this impossible because RC read lock doesn't affect the machine state. But the fact is it doesn't have to. It's not acting on the machine state, it's acting on the developer, on the guy programming it. The guy programming it is responsible for maintaining the rule, following the rule, saying that you don't do context switches inside RCU reside critical sections. And that action on the developer is what makes it work. In other words, what this is synchronization by social engineering. If you write RC read lock, the compiler doesn't even see it, right? The preprocessor throws it all away. It doesn't know. The CPU sure doesn't know. You know. And you have to follow the rule. You're not allowed to block inside a read side critical section. So RCU is in some sense synchronization via social engineering. Funny thing is that almost every other synchronization mechanism is as well. I mean, if you have a lock protected data structure, there's this social engineering thing that you're not supposed to mess with that data structure unless you hold the lock. All right, it's not like the lock kind of slaps you in the face if you don't grab it when you access it. It just doesn't protect it. So every synchronization mechanism involves social engineering. Every synchronization mechanism has rules. You are required to follow those rules for it to work. So in the case of locking, there's both machine state and social engineering components to it. RCU is a little unusual in that on the read side, there's only social engineering and not machine state. An exercise for you, if you're crazy enough, can you make a synchronization primitive that does only machine state changes without any social engineering? Let me know how it goes. And some other social engineering rules. Avoid data races is a big one recently. Protect specified variables with the corresponding lock. Access shared variables only within transactions. So all of those mechanisms have a social engineering aspect to them. This is a toy RCU implementation. I'm not going to go through it line by line. We've actually been through parts of it. We've been through the stuff up there. And it's about 20 lines of code. And what you do for synchronized RCU is you just go through every online CPU and run yourself on it. If you go and switch over to some other CPU, they'll force a context switch on that CPU. And so by the time you've gone through all the CPUs, everybody's on a context switch, you're done. 20 lines of code. And actually, it's only like 9 lines of code if you had a sequentially consistent machine. If it's a sequentially consistent machine, you could just use assignments instead of RCU to reference and RCU assign pointer. 20 lines of code, or 9, and sequentially consistent. You know something? People still insist that RCU is complicated. No idea why. So I'm going to skip the complex updates. I'm going to take a little bit of a look here. We had our definitions before. We got the same thing. And we had the RC read side critical section, the quiescent state, which is anywhere that's not a read side critical section. Extended quiescent state, which is just a long quiescent state. With a grace period, a time period when every thread's in at least one quiescent state, it ends when all the pre-existing readers complete, or sometimes after it. And it's guaranteed to complete in finite time as long as all RCU read cycle critical sections are finite duration. One of the nice things about this is you can have many readers piling through as you want, just back to back on every CPU on thousands of CPUs, and the update can still proceed deterministically because you only have to wait for the old readers, not the new ones, as long as the readers are finite in length. Of course, if you have infinite readers, well, you know, if you have infinite readers with writer lock, you got a problem too, right? Another piece of social engineering. You have to make sure that your critical sections are of reasonable size. Well, this leads to a question. I mean, suppose you have a read cycle critical section, you just keep extending it and try to make it go longer than a grace period. What would happen? Let's look at a picture of it. So we're trying to cheat with this reader. We're trying to make him go all the way across the grace period to be on both sides of it. If you tried to do that and you had a correctly working RCU, what would happen? No takers? Yeah. If you try to do this, what will really happen if your RCU is working is this. The grace period will just keep going until it covers the readers it needs to. So a grace period is not permitted to end, by definition, until all of the pre-existing readers have finished. So exactly right. And on the other hand, though, it's okay for the grace period to take longer than need be. Doesn't hurt anything. I mean, it might take longer, but... And the other thing that's okay, it's okay for it to start later than it needed to. Why would that be? Why would you want to do that? I'm sorry, I didn't hear you. What would be the use of starting the grace period later than you needed to and let it run longer than you needed to? Yeah, I mean, it doesn't hurt anything. I mean, it takes a little longer, but if all you're doing is freeing memory, maybe you don't care. But there's actually a big benefit you get out of it. And that is, if you have multiple updates, you can take care of both those updates with one grace period. And we take that to an extreme in the Linux kernel. There are certain workloads. For example, if you build a file system with tar and then remove it, and the file system has a lot of files in it, you can really easily get more than 1,000 updates per grace period, which means that the per update overhead of the grace period can be very, very small, which is one of the things that's helpful to it. We make heavy use of what we call batching. We take and we batch all the updates so that one grace period takes care of all of them. However, you can take a good thing too far, and there is a trade-off. I mean, starting the grace period later increases the number of updates, and it reduces the per update overhead, which is good. On the other hand, delaying the end of the grace period increases the latency. So if you really were waiting for it, if you're short of memory and need the memory to get back, that wouldn't be what you wanted. And also, if you increase the number of updates per grace period, you've got more memory waiting for the grace period. So you've increased the memory footprint. And but what that means is that starting grace period late and ending them late is a really good trade-off if you have memory is cheap and communication is expensive. And that's what happens in most modern systems. There's some embedded systems where you want to be a little bit more careful, but for most large servers, you got a lot of memory. And the cost of getting from one CPU to another is quite large, as we saw earlier. But still, as I said before, you can get too much of a good thing. And that's that it's okay for the system to yell at you or even abort the system if the grace period goes forever. So if some reader just keeps going on the Linux kernel, after 21 seconds, the Linux kernel starts complaining about that. And it's usually a software bug that causes it. Sometimes it's a problem in RCU, but most of the time it's that somebody did something silly, had an infinite loop in a read cycle critical section or something like that. Okay, at this point we're getting pretty close to the end. So what I'm going to do is fast forward through some of this stuff. We'll look at performance, and as you can see, with RCU, you're right down towards the theoretical limits. I mean, RCU read lock was free. RCU assign pointer, or excuse me, RCU dereference on most systems is just a load, and so you don't spend any extra overhead. Okay, well that's nice in theory. How about practice? So what we're doing is we're using Schrodinger's zoo, and we've got the bucket stuff we saw before, which went up. This is now log scale, so the curves look different shape. Log scale for both the lookups per millisecond and the number of CPUs. So bucket goes up and drops off. RCU and hazard pointer just continue scaling. RCU has a little bit of a drop off. You see the slope changes up there at about 32 CPUs, and that's because RCU is not quite as efficient about using the other thread as hazard pointers are. On the other hand, it started at heads, and hazard pointers just barely catch up. So we've got, in this case, instead of having this big fall off due to NUMA effects, if we can use RCU, we can get linear scaling and also really good performance. We're up almost a million, better part of a million lookups per millisecond there. That's what Schrodinger needs for scalability, not the stuff down there. The other thing, I said earlier there was a lot of interest in Schrodinger's cat. And per docket locking, so what we're doing here is we have 60 CPUs across, and what we're doing is we're varying the number of CPUs that are looking up the cat. So down here we just have random lookup. At the far end of the other side, everybody's looking up the cat and only the cat. And we just vary linearly through here. Well, RCU just goes flat, doesn't even notice. It can't tell the difference between looking up the cat or looking up randomly. Hazard pointers drops off slightly, and that's because hazard pointers requires memory barriers on the read side. And as the CPUs are accessing overlapping data, the CPU has to be more careful about the memory barriers, and it takes a little more overhead. Bucket locking collapses catastrophically at about 50 CPUs, and that's because everybody's looking up the cat, and there's only one lock protecting it, and so there's no parallelism. As you can see, it drops right back down to global locking, because if everybody's looking up at the cat, it essentially is a global lock. Okay, I think we can skip the real-time responses. That's my look on it. Free is a very good price. That was actually from a furniture salesman where I grew up, but I like the saying. And nothing is faster than doing nothing. Of course, RCU gets this speed by being specialized. It has a job it does that job very well, but it is specialized. So you want to use it where you read mostly and where some inconsistencies like when exactly was the cat born and died can be handled. That's where it works best. If things have to be consistent, like they are, for example, in the System 5 semaphores implementation in the Linux kernel, there's a little bit of overhead, but it works pretty well. So that's the green area. The yellow area is where you have a lot of updates, and you also require consistency. And this is the case, for example, for the directory cache lookup in the Linux kernel. And it might be okay, but you usually have to be very careful and use multiple mechanisms together to make it work and to make it scale well. You can get really good results, but it's nowhere near as natural as up there in the top. And if you need consistent data and you're almost always updating, you probably want to use something else. There are a couple of exceptions, but generally if you're in that stage, up here is where RCU's specialization is. If you're down there, use something else. Schrodinger's cat is up there in the blue. That's why it works so well. It is used quite a bit in the Linux kernel. It was introduced in late 2002, and we're almost 8,000. Actually, in the next release, we'll probably be a little bit over 8,000 uses of it. That's an absolute number. By comparison, there's about 100,000 uses of locking. But then that goes along with RCU being specialized and used in a fairly small number of places. So, summing up, synchronization overhead is a big issue for parallel programs. And we have some straightforward techniques to avoid this, partitioning the problem, avoiding inspection operations, and avoiding mutual exclusion. RCU is part of the solution. There are other things, hazard pointers, sequence locks, and so on. And it works really great where it's designed to work. It's good in other cases. But there comes a point where it decides it's had enough and somebody else takes over. There's a lot more information RCU available. I'm not going to go through this, but the slides will be available somewhere, and there's a bunch of different things we've had written on at various times. IBM Legal sponsors this slide. And if you remember only one thing from this talk, let it be this. Use the right tool for the job. Okay? If you use the right tool for the job, things will work fairly well. If you insist on using the wrong tool for the job, you've only got yourself to blame, right? So we're pretty close to the end of the hour. I could answer a few questions or whichever.
Any questions?
If not, let you get on with the afternoon. that much earlier. Thank you all very much for your time and attention. Some good points you raised during the talk, and again, hope you have as much fun with your end of computation as I've had with RCU. Thank you.